Hello everyone. This is the virtual presentation of our ICRA 2021 paper entitled Subsequent Keyframe Generation for Visual Servoing. This work has been carried out by the SIDE laboratory at the UTBM of the University of Technology Belfort-Montbéliard in France. First of all, I would like to introduce the context that led to the motivation behind this work. Our robotic team will participate for the second time to the Partner Robot Challenge during the World Robot Summit of this year. This challenge is composed of two different tasks that have to be autonomously performed by the Toyota human support robot. In the first one, the robot has to tidy up a messy room, sorting all objects in different storage spaces according to their category. In the second, the robot has to bring from the shelf a specific object that has been requested by a human. For both of them, the robot must be able to autonomously and accurately position its gripper with respect to an object in order to then interact with. The two most interesting sensors of the robot for this are the RGBD sensor on its head and a camera that are directly included in its gripper. The extraction of relatively small objects from a point cloud produced by the RGBD may be difficult or even impossible. That is why this work is focused on directly using the hand camera data to position the gripper with respect to a targeted object. Here is the summary of the presentation. Visual servoing seems to be an ideal solution to our problem since it is a well-studied closed-loop control method that uses visual data as feedback. Moreover, many contributions have been proposed over the years, such as new visual features modeling different control strategies, and more recently exploitation of deep learning has been investigated. However, it may be tricky to instantiate for real use case applications. For example, regarding our particular application, the robot must be able to position its hand camera with respect to a known object, but that may lie in different places. But visual servoing methods generally require a consistent known set of desired visual features that represents the desired camera pose, which is difficult to build when only a targeted object is known in the desired image while the rest of the scene remains unpredictable. At the same time, but in a different domain, generative adversarial networks become more and more efficient and are now able to generate sharp and realistic images, whether using image-to-image transfer approaches or image generation methods that are conditioned with a targeted pose. The goal of our work is to combine the advantages and efficiency of the visual servoing framework and the image generation ability of GAN. We propose a general pipeline composed of two interconnected parts. The first one, represented here in orange, is a classical pure photometric visual servoing. The Gauss-Newton control law estimates the camera velocities to regulate to zero the photometric error between the current acquired image I and the object-only image I. This single part can actually already work as it, but only if there is a significant photometric overlap between the two images. In other words, between the two views of the object itself, since nothing else is known in I/O. For this reason, we have integrated the subsequent keyframe generation part here drawn in blue. This part consists of a generative adversarial network that takes I and I/O as inputs and predicts an intermediate keyframe IK in between them. This generated keyframe is then considered as the desired photometric visual features. When the camera pose represented by this keyframe has been reached, a new one is generated when the process is repeated. To validate the general idea, we reduced the difficulty of the training by considering a single object and limiting the camera movement to 4 the 3 translations and the rotation around the camera optical axis. To facilitate its creation, we propose a strategy to automatically build a fully synthetic data set that covers a large volume above the targeted object. Background and lighting are randomly changed during the data creation to train a background agnostic GAN and robust to illumination changes. The size of the inverse pyramid that contains all the camera positions are computed accordingly to the object dimension. The keyframe pose, here colored in yellow, is computed in image space in order to ensure a sufficient photometric overlap between the object projection in high and high K. For example, the data set created for this playing toy is composed of about 600K triplets of images. Our GAN implementation is based on the official PyTorch Pix-to-Pix cycle GAN framework. We replaced the UNet generator and the batch normalization layers by respectively a RaiseNet9 generator and instance normalization. We also replaced the default loss by a Wasserstein GAN loss with gradient penalty. A training of 10 epochs with batch size of 60 took approximately 27 hours on our 600K triplets dataset. We first validated the proposed method in simulations. The ground appearance was randomly selected from a set of different textures including grass, concrete, wood, floor tiles, etc. Some of them contain strong patterns or visual repetitions, while some are more uniform. Of course, none of them has been seen by the GAN during the training stage. This video illustrates the behavior of the approach during these experiments. Here we can see the first keyframe generated by the GAN. This keyframe is used as a desired photometric features until the first convergence is reached. Then a new keyframe is generated, a new visual Servoing is launched, and so on. Despite the large initial displacement, the high difference between the initial and the object-only desired images, and in addition to important part in the latter that is totally unknown, the camera converged to the desired pose with a low final pose error. We have conducted many other experiments to validate the effectiveness of our GAN VS. Real experiments were then carried out using the HSR in different and known and uncontrolled real environments. This video illustrates the behavior of the approach during these experiments. While having been trained only on synthetic data, and even if no particular effort has been made on lighting conditions, GAN VS has similar behaviors in real experiment as in simulation. Indeed, GAN VS reconstructed complex details from the background of the real images, including strong patterns, specular highlights, and unknown objects. Although parts of the generated keyframes may sometimes appear blurry, the images contain sufficient data for the photometric visual Servoing to converge to the desired pose. Other real experiments have been conducted in different uncontrolled environments with various target object surroundings. Even with large initial displacements and high differences between the initial and the object-only desired images, the camera still converges to the desired pose. We presented GAN VS, a background agnostic method for positioning a camera with respect to an object. A dedicated GAN is used to predict intermediate visual keyframes between two images, allowing to converge towards a desired pose following subsequent photometric visual Servoing. In the future, we intend to extend this approach to 6DoF. Moreover, encouraging preliminary results seem to indicate that the generalization ability of GAN VS offers sufficient robustness to handle partial occlusions and to learn targeted objects. Thank you very much for your attention.